Hey everyone, on this lesson we are going to see some demonstrations using the pumping lemma. On the previous lesson, we introduced and presented this lemma, and we also saw an initial demonstration. Remember that we used this lemma to prove the non-regularity of languages, so that if I have a language L and I want to prove that this language is a non-regular language, then we can use the pumping lemma to do so, right? We also saw all of the conditions that we needed to satisfy in order to prove this. So on this lesson, we are going to see some demonstrations. We are going to see two demonstrations using the pumping lemma. The first one is this one. We need to prove that this language here, the language of the palindromes of even length, is a non-regular language, right? So in the same way, we need to prove that this language over the alphabet A and B, remember that we're using here the cleans closure, is a non-regular language. First of all, remember what the palindrome means. A palindrome is a word, number, phrase, or sequence that reads the same backwards as forwards, right? So for instance, if I have, for instance, the word W, this word W is equal to the word AB, B, BBA, for instance, then this word is a palindrome because it is the same that if we read backwards than forwards. If we read it forwards, we can read A, B, 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 A, and also if we read it backwards, we read A, B, 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 A, right? And in fact, we represent the palindrome language over the alphabet A and B. Keep in mind that we're working here over the alphabet A and B in this way. Keep in mind that when we have this R raised to a given word or given subword, this means the reverse. So essentially, if I have the word A, this word A is the word, or imagine the word B, this word is the word A, B, A, then the reverse of this word, B raised to R, is the same as the backwards of this, which is A, B, A, right? We have just reversed this word B. So why do we use this reverse notation to represent the palindrome language? Well, essentially because we can take this word that we know that this word belongs to the language L, and we can concatenate or represent this word W as U concatenated with U reversed, where U is this subword, and this word here, this subword, is U reversed. And this is true for all the words and all the palindrome words with even length. Keep in mind that this word has an even length. The length of this word is 6, right? We have 6 symbols. And so here, this is my subword U, and this is my subword U reversed. And you can see that for any word that belongs to this language L, we have this format. For instance, what if we take U to be the word or the subword BB, AB? Well, then this word W that needs to belong to the language L is going to have this format. So first we have U, which is B, B, A, B, and then we have the U reverse. So U reverse is this way. So we have here B, A, B, B. So this word is a word that belongs to the language L because we see that it is a palindrome word. It is the same that if we read it forwards as we read it backwards. As we can see, nothing really complicated. In fact, it is not the first time that we see the language of the palindromes with even length. We also saw this language previously on previous sections. So we need to prove that this language L is a non-regular language, so we will use the pumping lemma. Remember that in order to prove that a given language is a non-regular language, we need to take the contrapositive of these assumptions, and if we make the contrapositive, we arrive to these conditions of non-regularity. We explained this on the previous lesson. So here, first of all, for each or for any value n, any natural value n greater or equal to 1, there exists a word W that belongs to this language. So for instance, let's take this word W here to be the word A raised to this value n. Here we have that the value n is greater or equal to 1. It can be any value of natural numbers. Then also we have here bb, and then we have b raised to n, like so. And in fact, to make it even more interesting, let's just remain here the value n, like so. And even because then we will have to add another b at the initial and the beginning part. So if we have this word w, okay, first of all, this word, as we can see here, needs to belong to this language L. So does this word belongs to the language? The answer is yes, because this word is a palindrome word. It is the same as if we read it forwards than if we read it backwards. Okay, we have here n values of a, then we have 2 values of b, and then n values of a. Again, if we read it from right to left, we have the same. We start with n values of a, then we have 2 values of b, and then we have n values of a. In fact, here you can basically establish and represent that your value u, the subword u, is a raised to n concatenated with b, so that the reverse of u is the reverse of this, which is b concatenated with a raised to n. Right? So we have that this word is a word that belongs to this language L. So we begin properly with the conditions that we have here. Now, be any factorization of x, y, and z, which are subwords of this word w, such that the word w is the concatenation of all of them, and also the concatenation of x with y. The length of this is less or equal to the value n of this natural number n, and also the value of the length of y is greater or equal to 1. So this value y cannot be 0, right? The length of this subword needs to be at least 1. So for any factorization over and under the conditions of the pumping lemma, we are going to take this value x of this subword to be a raised to a given power j. Now remember, this is very fundamental but important that you remember, if I have a given symbol raised to a given value, imagine 3, if I have the terminal symbol a raised to 3, this is equivalent as the word a. So we repeat a 3 times. If I have 4 in here, this is the same as the word a, right? And the same is true for words, not only symbols. If I have, for instance, the word p, this is the word ab, and if I have p raised to 3, this is equal to ab. Okay, very important to remember. So we'll take the value of x to be this one on this demonstration, and also we'll take the value of y, of the subword y, to be a raised to this value k. Okay, so also remember the conditions under the pumping lemma. Okay, the concatenation of these two subwords needs to be less or equal to n, and the length of y needs to be greater or equal to 1. So essentially what this is saying is that this value k needs to be also greater or equal to 1, because if k is 0, if this was 0, then the length of y would be 0, and this is not possible. So k also is greater or equal to 1. So we can also here establish this condition k, which is the exponent here, is greater or equal to 1. And finally, remember that this word w is a word that needs to be represented in here as the concatenation of x, y, and z. And remember that this word w belongs to the language L and is this word. So if we have taken a and the value x to be a raised to j, the value I to be a raised to k, and we want a given value z such that if we concatenate them all we have this value, then it is trivial to see that z, this value z in here, okay, needs to be, let's put it in here, a raised to n minus j minus k, which are the values that we are adding in here, right? Then we have the two b's that we have in the word, and then we have a raised to n, like so. So as we can see, if we concatenate now x, y, and z, we have precisely this word w, right? Because a here, this j, this plus j with this minus j gets cancelled, this plus k with this minus k gets cancelled, and at the end we have a raised to n bb a raised to n, which is precisely the value w. Okay, it is not complex to see that when we concatenate x, y, z, we have a raised to j, which is x, we have a raised to k, which is y, and then we have a raised to n minus j minus k bb a raised to n. Keep in mind that they have the same base, so if we are concatenating them, this plus with this minus gets cancelled, this plus with this minus gets cancelled, and at the end we have a raised to n bb a raised to n, which is precisely w. So everything is alright. So with this configuration that we have represented, and also with this factorization of the word w, then to prove that the word, or in essence, to prove that this language is a non-regular language, we need to find the word, okay, when we raise this concatenation, but also this value y raised to a given exponent I, okay, if this word does not belong to the language, then we have the conclusion that L is a non-regular language. So the last thing that we need to do here, once we have all this, is we need to find the given exponent I greater or equal to 0, such that when we concatenate x, y, z, but also in the y subword, we raised this subword y to this value I, then this final word will not belong to the language L. If we can find this value I and we can see that this final word does not belong to the language L, then we will prove that this language L is a non-regular language, such that we have explained on the previous lesson, right? If we find this natural value I and this concatenation doesn't belong to the language L, then the language L is a non-regular language, right? Because it is going to violate the pumping lemma. So essentially, as we've said, we want a given value I such that when we concatenate x raised to, or in this case x concatenated with y concatenated with I, then this does not belong to the language L. So it is not complex to see here that any given value of I different from 1 will have this result. So we will achieve this result. The only value that I does not work, and at the end when we concatenate this will belong to L, is the case that we just saw before, when I is equal to 1. Because when I is equal to 1, we will have this word here, which is a word that belongs to the language L. But if this value I is different from 1, any other value different from 1 greater or equal to 0, okay, remember this condition in here, the value I needs to be greater or equal to 0, then for any value different from 1, we will have this conclusion and we'll achieve this result. Remember that it is an oath that you only find one value. If you find only one value of I, this is sufficient. You don't need to find all the values. In fact, we have here infinite values. So for instance, let's take the value I here to be 2. Okay, for this, we can also here could have chosen 0, but we are going to choose the value 2 on this example. So if I is 2, let's just apply this and see what we get at the end. So x concatenated with I raised to 2, right? So let's now apply this computation. Concatenated with z. So this is equal to x, which is a raised to j, concatenated with y, which is a raised to k. Keep in mind that if we have a raised to k concatenated with 2, or in this case raised to 2, this is equal to a, and we multiply, so we have 2k, right? So at the end, this is very important to know also, we have 2 times k, and then we have z, which is basically this expression in here. This is the value z, right? So z, we can see it is n minus j minus k concatenated with b, And here we don't need to put z, but we need to put the base a, which is the terminal symbol. So n minus j minus, let's put a very clear j, minus k, and then we have the two b's, and then we have the a raised to n, right? So what if we simplify this expression? We will have at the end a word that is palindrome. So will this word belong to the language L? Well, let's see. Okay, let's simplify this in here. So first of all, we see that this j here with this minus j, they are simplified because here I have a plus, here I have a minus, so they are gone. This 2k with this minus k, we have 2k minus k, this is only 1k, so at the end we have only 1k. So here the exponent of a is going to be a raised to n minus, or in this case, plus k, okay, which is basically 2k minus k, this is plus k, so this is the other exponent that we see here as a base a. Then we have the two b's, b, let's put it in here, k, 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 and we have the first b and the second b, and then we have here a raised to n. And this is the final word that we have at the end. Now, does this word belong to the language L? Is this word a palindrome word? The answer is no. This is clearly a non-palindrome word. It is very easy to see that here we have n minus k number of a's. Here we have the two b's, they are the same, so there's no problem. And then we have here n values of a. So we do not have a palindrome word. It is not the same if we read it forwards as if we read it backwards. Keep in mind, very important, this value k is at least 1. Okay, because if k is 0, then this k disappears and this is a palindrome word, but this k is at least 1. So there is no way we have the same amount of a's at the beginning as at the end. So here we have a number of a's that is greater than this number of a's. So we conclude that this word does not belong to the language L, right? This word does not belong to the language L, and hence, with this, we prove that L is not a regular language, which is the same. L is a non-regular language. Remember that you can see and download this solution on this demonstration 1 on the downloadable documents of this lesson. Again, here we have chosen a value I to be 2, but you also could have chosen any other value different from 1 and also greater or equal to 0, right? You could have chosen I to be 0, also I to be 3. In all of these cases, the resulting word that you'll get is going to be a word that is a non-palindrome word and so does not belong to the language L. Therefore, the language L is a non-regular language. And with this, we end this demonstration 1. Very well. Now we are going to use here and we are going to see a second demonstration, and the last demonstration for this lesson. We are going to prove using the pumping lemma that this language L that we have here 2 times the number of n, the number of a's, and then we have n times the value b and the symbol b, such that this value n is an even number. So we can also represent this language L in this way, as remember that this represents that the value n is a multiple of 2. So if n is an even number, then n is a multiple of 2, right? Some words that belong to this language, for instance, if n is equal to 1, for instance, this cannot happen because n needs to be a multiple of 2. So, for instance, if n is 2, we have this word w here, a raised to 2 times 2, this gives us a raised to 4, which is 4 times this value a, and then we have 2 times b, so we have this word. If the value of n is 4, then we will have here 8 times 8, or in this case, 8 times the symbol a, right, which is 2 times 4, and then we have 4 times the symbol b, right? So these are some words, for instance, that belong to this language L. So we need to prove that this language is a non-regular language, right? We are going to use the pumping lemma to do so. So here, for any value n greater or equal to 1, we are going to take the word w to be this word, a raised to 4 times n, concatenated with b times 2n. Keep in mind that this word is a word that belongs to this language. This is a word that belongs to this language because here we have 2 times the number of a's than the number of b's. So you can basically extrapolate and generalize this to be n, and here we can see this as 2 times n, right? So this word belongs to the language L. So once we have a word that belongs to this language L, keep in mind that the length of this word is also greater or equal to n. The length of this word is greater or equal to n. Okay, keep in mind that what is the precise length of this word, or the precise length we can see. And also this is uppercase. We can use this as uppercase, not in lowercase, right? So here we have 4 times n in uppercase concatenated with b, and here we have 2 times n uppercase. Yeah. So as we've explained, this word belongs to the language L because also one side we have that this word belongs to the language L because we have 2 times the number of a's to be the number of b's. Yeah, we have more a's than b's, precisely 2 times the number of b's. And then also the length of this word w, we can see it is 4n plus 2n. This gives us a value of 6 times n that is also greater or equal to n. This is true, right? So this first criteria here, that the length of this word is greater or equal to n, is satisfied as well. So here, for any given factorization of x, y, and z, okay, of this subword, let's take, for instance, the value x of this subword x to be a raised to j, the value y to be a raised to k, and then if we want the concatenation w x, y, z to belong to this word, keep in mind that we are representing this word w as the concatenation of x, y, z. So what needs to be the value of z? Well, this value of z needs to be precisely a raised to 4n that we start in here minus j minus k that we are adding with the x and the y, right? Concatenated with b to the power of 2 times n in uppercase. Again, keep in mind that if you do this concatenation, keep in mind that we are representing w as the concatenation of x, y, z. So what is going to be this concatenation? So we can see this is I, or in this case a raised to j, a raised to k, and then we have z, which is a raised to 4 times n minus j minus k, concatenated with b raised to 2 times n. So again, we can simplify this j with this j, this k with this k, and at the end we have here a raised to 4n concatenated with b raised to 2 times n, which is precisely the word w, right? So everything is alright, as we can see in here. Also, these two conditions, the length of xy needs to be less or equal to n, and the length of y greater or equal to 1. So with this conclusion, we see that if xy needs to be less or equal to n, we arrive to the conclusion that if here we have g occurrences of the symbol a, and here we have k occurrences of the symbol a, then we arrive also to another condition, which is j plus k needs to be less or equal to n, and also if here y, the length of y needs to be greater or equal to 1, if y is this, and here we have k occurrences, we also see that k needs to be greater or equal to 1. So the value of k is at least 1. So in other words, the subword y cannot be an empty word. Okay, we need to have at least one occurrence in this subword. Very well, so with all this criteria and all of this configuration, what do we need to find? Well, like in any pumping lemma demonstration, to prove the non-regularity, we need to find, as we can see here, a value I, this value of a natural value I, such that when we concatenate x with y raised to I concatenated with z, this does not belong to the language L, right? So we need to find this value I such that when we concatenate x with y raised to I with z, this must not belong to the language L. And it's not complex to see here that any value I that you choose here different from 1 is going to be the result that we want. Keep in mind the 1 cannot be, because if this is 1 is the same as not having anything, right? And keep in mind that x, y, z, if you concatenate x, y, z alone, you will have just w. And w is a word that belongs to the language L. And we want something that does not belong to the language L. So here you cannot choose I to be 1, but you can choose any other value greater or equal to 0, right? So here you can choose I equal to 0, you can choose I equal to 2. Keep in mind that the pumping lemma, what is saying that it only is sufficient that one value exists. Again, in this example, on this demonstration 2, we have infinite values, okay? But it is enough that only one value exists. If I have at least one value I, such that when we do this concatenation, this word, this resulting word does not belong to the language, then this is sufficient. So for this, we are going to take the value I to be equal to 0 for this example. So I, let's put it in here, is going to be equal to 0. And let's see what we have at the end. So let's do this concatenation. So we will have x concatenated with y raised to 0, concatenated with z. Keep in mind that when we raised y to 0, this is the empty word here, lambda, right? Any word or any subword, when you raise to 0, you have the empty word. And when we concatenate the empty word with the rest, we just have the rest. So we can simplify this as just having x concatenated with z, right? So what is x? Well, we can see that the value x is a raised to j. What is z? Well, z is a raised to 4n minus j minus k concatenated with b raised to 2 times n. So this is the value z, this is the value x, right? We can simplify this, as we can see. This j with this j disappears, right? So we have a, let's put it in here, a raised to 4n minus k concatenated with b raised to 2 times n. So we have this resulting word. Now we ask the student, is this word a word that belongs to this language L in here? Or in other words, do we have a word where the number of A's is 2 times the number of B's? And the answer is no, because here 2 times this value is 4n, but here we do not have 4n A's. We have 4n minus k number of A's. Keep in mind that this k cannot be 0. This k is at least 1, as we can see, under the pumping lemma condition. So if this value k is at least 1, it means that we have a number of A's that is not 2 times the number of B's. In other words, this resulting word here does not belong to the language L. And hence, if this word does not belong to the language L, then we arrive to the conclusion that this language is a non-regular language, right? Using the pumping lemma. Remember that you can check the solution on this demonstration too, on the downloadable documents of this lesson. Again, for this demonstration, we have used and we have chosen the value of I to be 0, but you could have chosen any other natural value greater than 0 or equal to 0 that is different from 1. The only value that here you cannot choose is the value 1, which is precisely the value that we use for representing this word w initially as the factorization of x, y, and z. So for any value I that you choose here different from 1, you'll see that you'll have and you will achieve a resulting word that will not belong to the language L. So the number of A's will not be 2 times the number of B's, and hence the language is a non-regular language. With this, we finish these demonstrations using the pumping lemma.